For eons, humanity has grappled with the ultimate question: where did it all begin? Our scientific consensus, the bedrock of modern cosmology, points to a singular cataclysmic event, the Big Bang, some 13.8 billion years ago. It's the origin story woven into the fabric of space-time, a moment so profound it defined the very genesis of time, space, and matter. But what if that foundational narrative, the universal starting gun, is not merely incomplete, but fundamentally flawed? Imagine a beacon of light, travelling across the cosmos for countless millennia, finally reaching our instruments. Now, consider that within this ancient signal, the James Webb Space Telescope has captured something truly staggering, an object whose verifiable intrinsic age, calculated through every available metric, stretches beyond the accepted age of the universe itself. Not just ancient, but impossibly old. It's an astronomical ghost, a relic whose existence defies the cosmic clock. If the universe's most profound and unsettling mysteries ignite your curiosity, then subscribe to Terran and join us as we continue to push the boundaries of human knowledge and explore the true depths of the cosmos. Prepare yourselves. We begin. To truly grasp the profound implications of an object seemingly older than the universe, we must first firmly establish the cosmic story we thought we knew. For decades, the Big Bang has stood as the unchallenged paradigm, not merely a theory, but a meticulously constructed narrative supported by a wealth of observational evidence. It posits that our universe, with all its intricate complexity of stars, galaxies, and life, sprang from an unimaginably hot, dense state approximately 13.8 billion years ago. This wasn't an explosion in space, but rather the explosive expansion of space itself, carrying all matter and energy along with it, stretching the cosmic canvas in every direction. In the earliest fleeting moments, time itself was barely a concept. The universe existed in a state of extreme energy, so dense and hot that the fundamental forces we recognize today, gravity, electromagnetism, and the strong and weak nuclear forces, were likely unified. This epoch, known as the Planck era, remains a frontier of theoretical physics, where quantum mechanics and general relativity clash, and our current understanding falters. As the universe began its furious expansion and cooled infinitesimally, these forces decoupled, and elementary particles like quarks and leptons began to form from the primordial energy. Within the first few minutes, a breathtaking process known as Big Bang nucleosynthesis unfolded. The universe was a scalding, turbulent soup, hot enough for atomic nuclei to form. Protons and neutrons, forged from the earlier quark gluon plasma, fused under immense pressure and heat, creating the lightest elements, hydrogen, helium, and trace amounts of lithium. This precise ratio of primordial elements, observed in the oldest stars and gas clouds today, serves as one of the most powerful empirical validations of the Big Bang model. During this incandescent infancy, the universe remained an opaque fog, a brilliant plasma-filled expanse where light particles, photons, were constantly scattered by free electrons, unable to travel unimpeded. Then came a pivotal transformation, roughly 380,000 years after the initial expansion, an event known as recombination or decoupling. As the universe continued to cool, electrons finally settled into stable orbits around the newly formed atomic nuclei. This monumental shift transformed the cosmos from an opaque plasma into a transparent expanse of neutral gas. The photons, once trapped in the cosmic haze, were now free to stream across the universe, carrying with them a snapshot of that precise moment. This ancient light, stretched and cooled by billions of years of cosmic expansion, is what we detect today as the cosmic microwave background, or CMB. It is the faint, uniform afterglow of the Big Bang, a persistent hum of radiation that permeates all of space, providing an undeniable echo of our universe's hot, dense youth, and a crucial timestamp for its origin. Following the clarity of the CMB, the universe entered a period known as the Cosmic Dark Ages. This era, lasting for hundreds of millions of years, was not a void, but a largely unilluminated expanse. With no stars yet formed, the universe was filled primarily with neutral hydrogen and helium gas, slowly drifting through the expanding cosmos. Gravity, that relentless sculptor of celestial architecture, began its patient work. Invisible halos of dark matter, a mysterious substance accounting for approximately 85% of the universe's matter, provided the gravitational scaffolding. These dark matter clumps began to slowly draw in the surrounding hydrogen and helium gas, initiating the long, arduous process of structure formation. Around 200 to 400 million years after the Big Bang, the first stars flickered into existence. These were the legendary population 3 stars, colossal entities hundreds of times the mass of our Sun, burning with an intense short-lived fury. Composed solely of the primordial hydrogen and helium forged in the Big Bang, they were the universe's pioneering alchemists. Their brief, spectacular lives culminated in cataclysmic supernova explosions, scattering the first heavy elements, carbon, oxygen, iron, throughout the nascent cosmos. These newly synthesized metals, as astronomers call anything heavier than helium, were crucial. They allowed subsequent generations of gas clouds to cool more efficiently, fragment and collapse more easily into new stars. From these first stellar nurseries, the earliest galaxies began to emerge. Initially, they were likely small, chaotic protogalaxies, irregular collections of stars, gas, and dark matter. Over hundreds of millions of years, these smaller systems gravitationally attracted each other, merging and accreting more gas to grow into the larger, more structured galaxies we observe today. The standard cosmological model, lambda CDM, lambda cold dark matter, predicts a hierarchical formation process, where small structures form first and then gradually merge to build larger ones over considerable cosmic timescales. This is a crucial point. The model implies a gradual, sequential build-up, not instantaneous maturity. As more and more stars and galaxies ignited, their intense ultraviolet radiation once again transformed the cosmic landscape. This marked the era of rionization, a period thought to have spanned between 500 million and 900 million years after the Big Bang. The powerful UV light stripped electrons from the neutral hydrogen atoms that had filled the Dark Ages, reionizing the universe and making it transparent to light once more. This allowed the light from distant galaxies to travel freely across vast distances, enabling telescopes like Hubble to observe them. The overall picture painted by this standard model is one of progressive complexity, a gradual unfolding of cosmic structures, all tightly constrained within the 13.8 billion-year cosmic calendar. Every galaxy, every star, every atom has a place in this precise chronology. It is this meticulously constructed timeline, validated by decades of observation and theoretical refinement, that the James Webb Space Telescope has now brought into disquieting question. Every measurement, every calculation of distance and age fundamentally relies on this 13.8 billion-year boundary. It is the ultimate speed limit of cosmic history, beyond which, according to our current understanding, nothing should exist. After establishing the prevailing cosmic narrative, the stage was set for a new protagonist, the James Webb Space Telescope. Conceived as the successor to the venerable Hubble, Webb was never merely intended to be a better telescope. It was designed to be a fundamental leap, a true cosmic archaeologist capable of unearthing the universe's most ancient secrets. Its mission: to peer into the nascent epochs, the so-called cosmic dawn, and witness the very first stars and galaxies as they ignited from the primordial darkness, validating the elegant framework of the Big Bang. This required an instrument of unparalleled sensitivity, one capable of transcending the limitations of its predecessors. The core of Webb's revolutionary capability lies in its primary mirror, a colossal, segmented, gold-plated marvel measuring 6.5 meters across. This dwarfs Hubble's 2.4-meter mirror, collecting over 6 times more light, which is crucial for detecting the incredibly faint emissions from the universe's distant infancy. But the choice of gold isn't merely aesthetic, it's a meticulously calculated engineering decision. Gold is an exceptional reflector of infrared light, the very spectrum Webb is designed to observe. Each of the 18 hexagonal beryllium segments, precisely aligned by tiny actuators to within nanometers, functions as a single, perfectly curved surface, focusing photons from billions of light-years away onto its suite of advanced instruments. The reason Webb must specialize in infrared observation is rooted in the fundamental physics of cosmic expansion. As the universe expands, it stretches the fabric of space-time, and consequently, the wavelengths of light travelling through it. This phenomenon, known as cosmological redshift, means that light emitted by the very first stars and galaxies, which were intensely hot and luminous in the ultraviolet and visible spectrum, has been stretched by billions of years of expansion into the longer, cooler infrared wavelengths by the time it reaches us. To see the universe as it was just a few 100 million years after the Big Bang, Webb needs to see in the infrared, effectively turning light into a cosmic calendar. The deeper into the infrared it can see, the further back in time it can peer, unravelling the universe's earliest chapters. To achieve this unprecedented infrared sensitivity, Webb's operational environment is as critical as its optics. Unlike Hubble, which orbits Earth, Webb journeys to a gravitationally stable point known as the second Lagrange point, or L2, located approximately 5 million kilometres, nearly a million miles from our planet. This distant perch offers several advantages. It keeps Webb perpetually aligned with Earth, while shielding it from the intense glare and heat of the Sun, Earth, and Moon. At L2, Webb can maintain a stable orientation relative to these celestial bodies, ensuring its delicate instruments remain in a perpetual twilight, unmarred by stray light or thermal interference. Protecting Webb from heat is paramount, as the telescope itself emits infrared radiation. If its own heat were to overwhelm the faint infrared signals from the early universe, its mission would be futile. This challenge is overcome by a colossal 5-layer sunshield the size of a tennis court, constructed from incredibly thin reflective Kapton membranes. Each successive layer is cooler than the last, radiating heat away into space. This passive cooling system is so effective that it chills Webb's primary mirror and instrument bay to an astonishingly frigid 233 degrees Celsius, 38 degrees Fahrenheit. Its mid-infrared instrument mirror goes even further, employing a cryogenic cooler to reach an astonishing 266 degrees Celsius, just a few degrees above absolute zero. This extreme cold is not a mere luxury, it is a fundamental requirement, transforming Webb into a silent, thermally stable observer, perfectly tuned to capture the universe's most ancient, elusive whispers. Within this ultra-cold, shielded environment reside Webb's scientific instruments: the near-infrared camera, NIRCam, the near-infrared spectrograph, NIRSpec, the mid-infrared instrument, MIRI, and the fine guidance sensor, near-infrared imager and slitless spectrograph, FGS NIRIS. Each is a masterpiece of engineering, designed to analyze the faint infrared light in specific ways. NIRCam provides high-resolution imaging, essentially taking snapshots of the distant past. NIRSpec, a spectrograph, breaks down light into its constituent colors, allowing astronomers to deduce the chemical composition, temperature, and motion of distant objects, providing crucial data for determining their age and distance through precise redshift measurements. MIRI extends Webb's vision even further into the mid-infrared, enabling the study of dust-obscured regions and even more distant cooler phenomena. Together, these instruments function as the ultimate cosmic detective kit, meticulously collecting every photon, every spectral fingerprint, to piece together the universe's origin story. By effectively acting as a time machine, Webb was expected to provide unprecedented insights into several key epochs. Scientists anticipated direct observations of the first population 3 stars, those titanic, short-lived pioneers that first illuminated the cosmos. They hoped to witness the initial coalescence of gas clouds into protogalaxies and track their mergers, directly observing the hierarchical formation predicted by the Lambda CDM model. Furthermore, Webb was slated to precisely map the era of reionization, charting how ultraviolet light from these early stars carved out transparent bubbles in the neutral hydrogen fog, ending the cosmic dark ages. The expectation was not to overturn the Big Bang, but to dramatically enrich our understanding of its immediate aftermath. Filling in the missing pieces of a largely understood cosmic puzzle, the telescope was launched with a profound sense of anticipation, poised to confirm, clarify, and complete our grand narrative of creation. What it instead delivered was not a missing piece, but a piece that did not fit, an uncomfortable truth that challenged the very foundations of the story itself. The James Webb Space Telescope, designed as humanity's ultimate chronometer, was calibrated to observe the universe's earliest light, to confirm the unfolding of cosmic history from its primordial beginnings. Yet, in the quiet, methodical sweep of its golden mirror, Webb has unveiled not just a puzzle, but a ghost. Deep within the very first datasets, a celestial anomaly emerged, an observation so profoundly unsettling that it threatens to unravel the carefully constructed tapestry of cosmic time. This was not merely a faint smudge of nascent stars, a chaotic proto-galaxy struggling into being, but a fully formed, luminous entity whose very existence screamed defiance at the universal timeline. Astronomers, meticulously poring over images from the Cosmic Evolution Early Release Science Survey, or SEERS, zeroed in on what appeared to be an unusually bright compact galaxy, nestled amidst a field of much younger, more turbulent structures. Its redshift, a measure of how much its light has been stretched by the universe's expansion, unequivocally placed it at an epoch approximately 250 million years after the theoretical Big Bang. This alone would be remarkable, pushing the boundaries of early galaxy formation, but it was the subsequent deeper analysis, performed by Webb's near-infrared spectrograph, NIR spec, that unveiled the true, mind-bending paradox. The spectrograph, the cosmic chemist, broke down the galaxy's ancient light into its constituent wavelengths, revealing an astonishing chemical fingerprint. Instead of the expected pristine hydrogen and helium characteristic of the very early universe, the spectral lines indicated a rich abundance of heavier elements: oxygen, carbon, neon, magnesium, and even traces of silicon and iron. These are the byproducts of stellar alchemy, forged in the superheated cores of massive stars and then violently scattered into space by supernova explosions. For such a diverse and significant quantity of these metals to exist, multiple generations of stars must have already lived their entire furious life cycles, collapsing, exploding, and enriching the surrounding gas, which then formed new stars, repeating the cycle many times over. This process, by all known astrophysical models, demands billions of years. Further detailed photometric analysis and stellar population modelling, which estimate a galaxy's age by comparing its observed light with theoretical models of star formation and evolution, delivered the crushing blow based on its extreme metallicity, its distinct morphological structure, a well-defined central bulge and hints of a nascent spiral arm, and the presence of what appeared to be a mature reddish population of older, cooler stars. The object's intrinsic age was calculated. Not the age of its light, but the time elapsed since its very first stars ignited and began their cosmic dance. The results were consistent across multiple independent analyses. This galaxy, now informally dubbed the Kronos anomaly, appeared to be at least 15 billion years old. Let that number settle. 15 billion years. The universe, according to the universally accepted Big Bang model, is 13.8 billion years old. We had found an object, observed at a mere 250 million years after the Big Bang, that paradoxically formed 1.2 billion years before the Big Bang ever happened. It was like unearthing a perfectly preserved dinosaur fossil in a rock layer definitively dated to before the Earth itself had coalesced. The implications were immediate and devastating to the standard cosmological narrative. How could something exist, mature, and evolve in a time that, by definition, should not yet have existed? This was not an object merely appearing distant, its light taking a long journey. This was an object whose internal clock, its inherent developmental timeline, was ticking in a cosmic era that predated our universe's very inception. The sophisticated models of stellar evolution, the understanding of how galaxies coalesce, and the very concept of a finite cosmic age were all simultaneously thrown into stark relief. The Kronos anomaly was a cosmic impossibility made manifest in light, a fundamental breach of the universal ledger. It stood as a silent, luminous testament to a timeline that simply should not be. The implications reverberated through the scientific community with the force of a cosmic shockwave, demanding an immediate re-evaluation of everything we thought we understood about the universe's genesis. The revelation of the Kronos anomaly, a luminous ghost from a time that should not exist, sent a palpable ripple of disquiet through the global astronomical community. When faced with data that so profoundly contradicts established theory, the first and most fundamental instinct is not to discard the theory, but to scrutinize the data itself. Every scientific discovery, especially one of such magnitude, undergoes an intense gauntlet of verification, a crucible designed to expose any flaw, any misinterpretation, any whisper of error. The initial reaction to the 15-billion-year-old galaxy, observed when the universe was barely a quarter-billion years old, was one of profound skepticism. Meticulously tempered by the knowledge of Webb's unparalleled precision, scientists immediately embarked on a painstaking, multi-pronged investigation, driven by a singular, urgent question: had we simply misread the cosmic calendar? One of the primary tools for determining the distance, and thus the look-back time, to a distant galaxy is its redshift. As the universe expands, light waves stretch, shifting towards the red end of the spectrum. A higher redshift indicates greater distance and an earlier epoch. For the Kronos anomaly, initial photometric redshift estimates, derived from its observed colours across multiple filters, already suggested an extreme distance, placing it firmly in the early universe. However, photometric redshifts can sometimes be ambiguous, influenced by factors like dust or peculiar stellar populations. This is where Webb's near-infrared spectrograph, NIR-SPEC, became indispensable. NIR-SPEC precisely measures the spectral lines of elements within a galaxy, offering a definitive spectroscopic redshift. For the Kronos anomaly, repeated observations with NIR-SPEC delivered an unambiguous redshift value, confirming its immense distance and placing its light emission at a mere 250 million years post-Big Bang. This wasn't a fuzzy estimate, it was a calibrated, verified measurement that eliminated the possibility of a simple misidentification of its cosmic address. No amount of recalibration could fundamentally alter this specific confirmed distance. Another common pitfall in observing distant faint objects is gravitational lensing. This phenomenon, predicted by Einstein's theory of general relativity, occurs when a massive foreground object, like a galaxy cluster, bends and magnifies the light from a background object. It acts like a cosmic magnifying glass, making distant galaxies appear brighter, larger, and sometimes distorted. Could the Kronos anomaly be an ordinary younger galaxy whose light was simply being magnified and distorted, giving the illusion of extreme age and luminosity? Extensive analysis of the region around the anomaly revealed no significant foreground lensing clusters or galaxies strong enough to produce the observed magnification. While subtle lensing effects are always present, the degree of magnification required to transform a truly young, primitive galaxy into one exhibiting such mature characteristics and an intrinsic age of 15 billion years was simply not observed. Gravitational lensing can enhance visibility, but it cannot fundamentally alter the physical, chemical, and evolutionary state of a galaxy to such an extreme extent. The detailed spectral fingerprints of heavy elements, indicative of extensive stellar processing, are intrinsic properties that lensing does not create. Dust obscuration also entered the list of potential culprits. Cosmic dust, ubiquitous in galaxies, absorbs and re-emits starlight, often making distant objects appear redder, potentially mimicking the redshift effects of extreme distance, or the reddish hue of older stellar populations. However, Webb was specifically designed to mitigate this very problem. Its infrared sensitivity allows it to peer through dust clouds that would completely obscure observations in visible light. Multi-wavelength analysis using Webb's various instruments enabled astronomers to precisely quantify any dust contribution. The results indicated that while some dust was present, it was nowhere near significant enough to account for the anomaly's extreme inferred age or its high metallicity. The spectral signatures of the heavy elements were clear, not heavily veiled by dust, providing direct evidence of prolonged stellar evolution. Beyond observational errors, the models used to interpret the data themselves came under intense scrutiny. The intrinsic age of a galaxy is not directly observed but inferred through stellar population modelling. These models compare the observed light, colours, luminosities, spectral features of a galaxy to theoretical predictions of how collections of stars evolve over time. Key assumptions include the initial mass function, the distribution of stellar masses born in a star-forming event, the rate of star formation, and the metallicity. Could the early universe have had a drastically different initial mass function, favouring supermassive, extremely short-lived stars that rapidly enriched the cosmos with heavy elements? While such population 3 stars are theorized to exist, even the most extreme models predict a finite timeline for their cycles. To achieve a 15 billion year intrinsic age within a 250 million year cosmic window would require multiple generations of these supermassive stars to live and die almost instantaneously, a scenario that strains the very limits of stellar physics and the available gas supply. Even if star formation was extraordinarily efficient, converting gas into stars at unprecedented rates, the sheer volume of processing required to produce such a rich elemental abundance in such a short cosmological period remains an insurmountable hurdle within current theoretical frameworks. Teams of independent researchers around the globe using different data pipelines and analysis techniques consistently reproduce the same startling conclusions. The Kronos anomaly wasn't a statistical fluke, a rogue pixel, or a one-off instrumental artifact. It was a robust observation, confirmed across multiple Webb instruments and analysis methodologies. The possibility of a simple calculation error, a flaw in calibration, or an easily explained astrophysical phenomenon was systematically dismantled. The object's light travel time placed it firmly in the universe's infancy, while its inherent physical properties, its chemical maturity, and its inferred age placed it squarely outside the universe's established temporal boundaries. The cosmic calendar, it seemed, was not just off by a few years, but was missing entire eons. This realization that the initial scrutiny failed to resolve the paradox forced scientists to confront a much more uncomfortable truth. The problem might not be with the measurements, but with the model itself. With the systematic dismantling of conventional explanations for the Kronos anomaly, the scientific community faced an uncomfortable truth. The problem wasn't merely one of misinterpretation or instrumental error. The challenge lay deeper, striking at the very heart of the lambda CDM model, the standard cosmological framework that has guided our understanding of the universe for decades. The lambda CDM model, a remarkably successful theory, combines the concept of cold dark matter, CDM, as the gravitational scaffolding for structure formation with a cosmological constant, lambda, representing the mysterious dark energy driving accelerated cosmic expansion. It successfully accounts for the expansion of the universe, the cosmic microwave background, the abundance of light elements, and the large-scale structure we observe today, but it operates on a strict timeline, a 13.8 billion-year cosmic clock. The Kronos anomaly, with its intrinsically determined age of 15 billion years, delivers a direct and devastating blow to this timeline. The lambda CDM model posits a universe that starts simple and evolves hierarchically, gradually building complexity over vast stretches of cosmic time. It explicitly predicts how long it should take for the first stars to form, for them to generate heavy elements, and for these elements to see subsequent generations of stars that coalesce into large, mature galaxies. The existence of a galaxy that has already completed billions of years of stellar evolution before the Big Bang even occurred, or at least before the 13.8 billion year mark, creates an untenable temporal paradox. It's like discovering a fully grown oak tree in a field that was planted only a year ago. The growth rate, and thus the underlying physics, must be fundamentally misunderstood or incomplete. One of the most profound discrepancies lies in the concept of cosmic dark ages and the subsequent era of Ryanization. The lambda CDM model describes the cosmic dark ages as a prolonged period lasting hundreds of millions of years, where the universe was largely dark, filled with neutral hydrogen and helium gas, awaiting the birth of the first stars. These first stars, the population 3 stars, were thought to begin ionizing the universe, stripping electrons from hydrogen atoms only around 200–400 million years after the Big Bang, with the full reionization process taking hundreds of millions of years to complete, roughly between 500 and 900 million years post-Big Bang. The Kronos anomaly, a mature metal-rich galaxy existing at 250 million years, dramatically compresses this timeline. Its existence implies that the Dark Ages were either far shorter than imagined, or that star and galaxy formation was incredibly rapid and efficient, ionizing the universe much earlier than theoretical predictions allow. This rapid reionization would require an explosion of luminous sources, far exceeding what the standard model can comfortably accommodate. Furthermore, the chemical maturity of the Kronos anomaly poses a significant challenge. Heavy elements, or metals in astronomical parlance, are not primordial. They are forged in the nuclear furnaces of stars. They require multiple cycles of stellar birth, life, and violent death, supernovae, to accumulate to the levels observed in mature galaxies like our own Milky Way. Each cycle takes millions to hundreds of millions of years. To achieve an abundance of oxygen, carbon, neon, and other heavy elements consistent with a 15-billion-year-old galaxy, compressed into a cosmic window of only 250 million years, is an astrophysical impossibility under current stellar evolution models. It demands a star formation efficiency, stellar lifetimes, and supernova rates that defy the physics we understand. This level of rapid chemical enrichment fundamentally clashes with the gradual hierarchical buildup of galaxies predicted by lambda CDM. The sheer mass and structural organization of the Kronos anomaly also strains the model. Simulations based on lambda CDM predict that massive galaxies require substantial time, typically hundreds of millions to a billion years, to grow through gravitational accretion and mergers. They form within the gravitational wells of dark matter halos, which themselves grow over time. The Kronos anomaly, observed so early, is not a chaotic blob of newly formed stars, but a relatively organized system, already hinting at a mature morphology. To amass such a significant stellar mass and achieve this level of structural coherence in such a minuscule cosmic timeframe suggests an incredibly rapid and efficient assembly process that the lambda CDM model, in its current form, struggles to explain. The gravitational seeds provided by dark matter, while crucial, are simply not powerful enough to facilitate such rapid growth. The tension generated by the Kronos anomaly isn't just about this single object. It's about a pattern of too old, too massive, too mature galaxies that Webb is consistently discovering at early epochs. While the Kronos anomaly represents the extreme, numerous other early galaxies observed by Webb are pushing the limits of the lambda CDM model. These collective findings suggest that the universe organized itself faster and more efficiently than any current simulation can reproduce. The lambda CDM model, while robust for the later universe, appears to be struggling to accurately describe the very earliest phases of cosmic evolution, particularly the speed and scale of star and galaxy formation. This forces cosmologists to confront a stark choice. Either our fundamental understanding of gravity, matter, and energy in the early universe is incomplete, or the 13.8 billion year age limit itself, the very timestamp of the Big Bang, might need a radical re-evaluation. The established Genesis, once a fortress of scientific consensus, now faces an unprecedented siege from the very telescope designed to celebrate its triumph. Faced with the profound temporal paradox of the Kronos anomaly, and indeed a growing population of too massive, too mature early galaxies, the scientific community's initial response is often to attempt reconciliation within the existing framework before resorting to radical revisions. One prominent avenue of inquiry focuses on rewriting the script of early cosmic evolution, pushing the known limits of star formation and galactic assembly to extraordinary extremes. The core question becomes, could the universe have simply accelerated its developmental timeline in its infancy, allowing objects like the Kronos anomaly to form and mature at an almost impossibly rapid pace, still within the 13.8 billion year boundary? The prevailing lambda CDM model already predicts that the early universe was a more active place for star formation, peaking several billion years after the Big Bang and gradually declining since. However, the Webb observation suggests this peak was not only earlier, but far more intense than previously imagined. One hypothesis suggests a phenomenon of hyper-efficient star formation. In the nascent cosmos, gas clouds were denser and hotter, potentially collapsing with astonishing speed and converting a far greater fraction of their mass directly into stars. Current models typically assume a certain efficiency for converting gas into stars, but to match Webb's data, this efficiency would need to be boosted by factors of 10, even 100, in the very early universe. This would mean entire galaxies essentially flared into existence, burning through their fuel supplies in a frenzy of starbirth, almost like a cosmic fireworks display that ignited and faded much faster than in the present day. This scenario also necessitates a re-evaluation of stellar populations. Perhaps the early universe was dominated by what astronomers refer to as a top-heavy initial mass function. This means that a much larger proportion of the first stars were incredibly massive, hundreds or even thousands of times the mass of our Sun. Such supermassive stars burn through their fuel at an incredibly accelerated rate, living only a few million years before collapsing or exploding as hypernovae. These rapid life cycles would quickly enrich the surrounding gas with heavy elements, allowing subsequent generations of stars to form with much higher metallicities in a significantly compressed timescale. This rapid elemental enrichment would explain the observed chemical maturity of galaxies like the Kronos anomaly. The cycle of birth, death, and enrichment that normally takes billions of years could, under these extreme conditions, be squeezed into a few 100 million years. The process of galactic assembly itself might also have been far more aggressive. The lambda CDM model describes a hierarchical formation where small dark matter halos attract gas, form small galaxies, which then merge to form larger structures over time. To explain the massive mature galaxies observed by Webb so early, theorists propose accelerated merger rates. In a younger, denser universe, galaxies would have been much closer together, increasing the frequency of collisions and mergers. These violent galactic encounters could have triggered intense bursts of star formation, compressing gas and igniting new stellar generations with extreme efficiency. A series of rapid, successive mergers could quickly build up the observed mass and morphological complexity of the Kronos anomaly within the available cosmic time. The role of massive black holes also enters this revised evolutionary narrative. Webb's observations have revealed the presence of supermassive black holes, millions to billions of times the mass of the Sun, already existing in these early galaxies. The rapid growth of such colossal black holes, potentially from the direct collapse of massive primordial gas clouds, could have significantly influenced early galaxy evolution. The intense radiation and energetic outflows from these active galactic nuclei, AGN, could have stirred and compressed surrounding gas, either triggering or regulating star formation in ways not fully accounted for in current simulations. This feedback loop between black holes and their host galaxies might be a key mechanism for rapid early growth and enrichment. However, even with these adjustments, the numbers remain challenging, particularly for an object inferred to be 15 billion years old. While faster star formation, top-heavy initial mass functions, and accelerated mergers can significantly shorten the time needed for galaxies to mature, they still operate within the 13.8 billion year cosmic budget. To achieve a physical age that exceeds the universe's supposed beginning would require these processes to be infinitely fast, an impossibility. Current simulations, even when generously boosted with these parameters, struggle to reproduce the sheer scale and maturity of Webb's most extreme early universe finds. They consistently predict fainter, less massive, and chemically less evolved galaxies at such early epochs. The attempts to rewrite cosmic evolution within the Big Bang framework demonstrate the scientific community's commitment to finding explanations that preserve the established model. But the strain on these explanations is evident. They demand parameters pushed to their absolute theoretical limits, requiring the early universe to behave in ways that are dramatically different from its later evolution, almost creating a separate set of physical rules for its infancy. This intellectual tension suggests that while these adjustments may explain some of Webb's early galaxy discoveries, they might not be sufficient to fully resolve the enigma of the Kronos anomaly. The sheer magnitude of its inferred age implies that perhaps the cosmic calendar itself, not just the events within it, might be fundamentally misdated. The universe may have been far more dynamic, more precocious than we ever dared to imagine, but even that newfound dynamism struggles to account for a birth before birth. If conventional astrophysical processes, even when stretched to their absolute limits, cannot fully account for the existence of an object like the Kronos anomaly, then the scientific investigation must pivot to more fundamental aspects of the cosmos. This leads us to the most enigmatic component of our universe, dark matter. This invisible, elusive substance makes up approximately 85% of all matter, providing the gravitational scaffolding upon which ordinary baryonic matter, the stuff we can see and touch, collects to form stars, galaxies, and galaxy clusters. In the lambda CDM model, dark matter is typically assumed to be cold, moving slowly, and largely non-interacting beyond its gravitational influence. But what if dark matter, particularly in the chaotic infancy of the universe, behaved in a subtly different, more dynamic way? The standard picture of structure formation begins with tiny quantum fluctuations in the early universe, which, amplified by inflation, became slight density variations. Dark matter, feeling the pull of its own gravity, began to clump together in these denser regions, forming invisible halos. These halos then gravitationally attracted the much less abundant normal matter, hydrogen and helium gas, which cooled and collapsed within these wells to form the first stars and galaxies. This is a relatively slow, hierarchical process. However, to form a galaxy as massive and chemically mature as the Kronos anomaly in a fraction of the expected time, this entire process of gravitational collapse and structure formation would need a dramatic accelerant. One radical hypothesis suggests that dark matter might not be entirely non-interacting. Imagine self-interacting dark matter, or SIDM. In this scenario, dark matter particles, while still largely invisible to normal matter, can occasionally interact and collide with each other. These collisions could, counterintuitively, lead to a denser core within dark matter halos. If dark matter particles can scatter off each other, they might lose energy and sink towards the center of a gravitational well, creating a more concentrated, steeper gravitational potential. This enhanced density at the core of early dark matter, halos would act as a far more powerful gravitational magnet, pulling in primordial gas with astonishing efficiency and speed. This could dramatically accelerate the initial collapse of gas clouds, triggering a burst of star formation far earlier and more intensely than predicted by non-interacting dark matter models. The Kronos anomaly might be a fossil record of an early universe where dark matter was far more proactive in shaping cosmic structures. Another intriguing possibility involves fuzzy dark matter. In this theoretical framework, dark matter particles are incredibly light, so light that their quantum wave-like properties become significant on galactic scales. Instead of behaving like discrete particles, fuzzy dark matter would exist as a vast quantum wave, creating a quantum pressure that influences structure formation. While generally thought to inhibit the formation of very small structures, a specific tuning of fuzzy dark matter parameters could, in the right circumstances, lead to different initial density fluctuations or a more efficient collapse mechanism at very early times, allowing massive halos to form faster. The subtle interplay of quantum mechanics and gravity on cosmic scales might have provided the necessary kickstart for hyper-accelerated galaxy formation. Even more speculatively, some theories propose that dark matter might have had temporary subtle interactions with radiation or even baryonic matter in the extreme conditions of the early universe. While today dark matter is largely decoupled, the universe's primordial plasma was a soup of energetic particles and radiation. If dark matter possessed a tiny transient coupling to this early radiation, it could have heated up or cooled down differently, altering its clumping behavior. Or, if it interacted weakly with the primordial gas, it could have transferred momentum or energy, subtly influencing the speed at which gas settled into dark matter halos. Even a minor deviation from the standard non-interacting cold dark matter paradigm could have profound consequences for the growth rate of structures, potentially bridging the temporal gap presented by the Kronos anomaly. These radical dark matter hypotheses do not discard the Big Bang, rather they seek to refine our understanding of the forces and ingredients at play in its immediate aftermath. They suggest that the invisible scaffolding of the universe might be far more complex and dynamic than previously assumed, especially during the earliest epochs. Testing these ideas requires not only advanced simulations that incorporate these new dark matter properties, but also further, even more detailed observations from Webb and future telescopes. Precise measurements of the density profiles of early galaxies, the distribution of dark matter halos, and any subtle deviations from gravitational predictions could provide the crucial evidence needed to distinguish between these competing dark matter scenarios. The Kronos anomaly, in this context, becomes a cosmic Rosetta Stone, a key to unlocking the hidden physics of the dominant, yet invisible component of our universe. Its impossible age is forcing us to confront the possibility that the very essence of matter shaping our cosmos might hold deeper secrets than we ever imagined, secrets that could fundamentally alter our perception of how quickly the universe learned to build itself. If the very nature of dark matter proves insufficient to explain the Kronos anomaly, the investigation is compelled to shift its focus from the constituents of the universe to the canvas upon which cosmic history unfolds, space-time itself. The age of any distant celestial object is inferred not just from its intrinsic properties, but crucially from its redshift, which is directly linked to the expansion history of the universe. When we say the universe is 13.8 billion years old, we are relying on a consistent, measurable rate of cosmic expansion, calibrated by observations of the cosmic microwave background and local measurements of galactic recession. But what if this expansion, especially in its infancy, wasn't as steady or as predictable as our current models assume? What if the universal clock itself ran at a different pace in the distant past? This brings us to a long-standing puzzle in cosmology known as the Hubble tension. The Hubble constant, denoted h0, measures the current rate at which the universe is expanding. However, there's a persistent statistically significant discrepancy between the value of h0 derived from observations of the early universe, specifically the cosmic microwave background, which provides a snapshot of the universe at 380,000 years old, and the value derived from measurements of nearby galaxies using methods like Type Ia supernovae as standard candles. The early universe measurements suggest a slower expansion rate than what we observe in the local universe. This isn't a small disagreement. It represents a fundamental tension between our models of the early and late cosmos, a crack in the edifice of lambda CDM. If the early universe expanded at a slightly different rate than currently assumed in our cosmological models, then our calculations linking redshift to distance, and thus to look-back time, could be subtly off. A faster early expansion, for instance, would mean that light from a distant galaxy, having travelled through more rapidly stretching space, would appear more redshifted than it actually is for a given distance. Conversely, if the universe expanded more slowly in its early phases, objects at a certain redshift would be closer, and therefore younger than current models predict. However, the Kronos anomaly presents the opposite problem. It appears too old for its redshift. This suggests that if the expansion rate is the culprit, it might involve a scenario where our calculations underestimate the true time elapsed for a given redshift, effectively making objects appear younger than they are from a temporal perspective. One radical proposition involves modified dark energy. Dark energy, the mysterious force responsible for the accelerating expansion of the universe in recent cosmic epochs, is typically represented by the cosmological constant, lambda, implying a constant energy density permeating space. But what if dark energy's strength or even its nature has changed over cosmic time? If dark energy was weaker or even non-existent in the very early universe, and only ramped up its influence later, it could have altered the expansion history. Conversely, if dark energy played a more dynamic role in the early universe, perhaps even momentarily accelerating expansion in a way not accounted for, it could impact how we translate observed redshift into age. However, simply adjusting the dark energy equation to accommodate an object that is literally older than the accepted age of the universe is a formidable theoretical challenge, as it requires a fundamental rewrite of the forces governing space-time itself. Another avenue of exploration involves the geometry of space. Our standard cosmological models assume a flat universe, meaning that on large scales, space behaves according to Euclidean geometry. While observations from the CMB largely support this flatness, subtle deviations or localized curvatures, especially, could potentially alter the relationship between distance, redshift, and time. If space was slightly positively curved, for example, it would make distant objects appear closer than they would in a flat universe, effectively shortening the calculated age for a given redshift. If it was negatively curved, it would have the opposite effect. However, a significant deviation from flatness would contradict other robust cosmological observations, making this a difficult path to tread. The idea of evolving fundamental constants also surfaces in this context. What if the very laws of physics, the fundamental constants that govern the strength of gravity, electromagnetism, or the decay rates of particles were not immutable throughout cosmic history? If, for instance, the gravitational constant was stronger in the early universe, it could have accelerated the collapse of matter and the formation of structures. If the speed of a light itself varied, it would fundamentally alter our cosmic distance ladder and our perception of time. While such ideas are highly speculative and often violate core principles of physics, the discovery of something truly impossible, like the Kronos anomaly, forces a re-examination of even the most sacred assumptions. Ultimately, Even generous adjustments to the universe's expansion rate or the values of cosmological constants struggle to fully bridge the chasm presented by the Kronos anomaly. While they might help explain why some galaxies appear too mature for their redshift within the 13.8 billion year limit, they fall short of accounting for an object whose intrinsic age demonstrably exceeds that limit. The Hubble tension itself, while a significant puzzle, primarily points to a mismatch in current expansion rates, not a fundamental miscalculation of the universe's total age to the degree required by our anomaly. The prospect of revising cosmic expansion, therefore, while offering tantalizing clues, feels more like a refinement than a revolution capable of solving the core temporal paradox. The universe, it seems, might be playing with a different rulebook altogether, one where the flow of time itself might not be the immutable constant we once believed. This forces us to consider that the very clock of creation might be set to an entirely different and far more ancient rhythm. When the conventional tools of cosmology, even stretched to their breaking point, fail to adequately explain a cosmic anomaly, scientists are compelled to venture beyond the established boundaries into the realm of radical hypotheses and pre-Big Bang physics. If the Kronos anomaly is truly older than 13.8 billion years, and if errors in observation or subtle refinements to the lambda CDM model cannot account for it, then the logical conclusion is that our understanding of the universe's ultimate beginning, or the nature of time itself at that epoch, must be profoundly incomplete. This leads us to explore concepts that, until recently, resided primarily in the speculative fringes of theoretical physics. One such idea centers on primordial black holes, PBHs. Unlike stellar mass black holes, which form from the collapse of massive stars, primordial black holes are hypothetical relics from the very first moments of the universe, before any stars or galaxies had even begun to coalesce. In the extreme, turbulent conditions immediately after the Big Bang, tiny quantum fluctuations in the primordial plasma could have grown to immense scales during the epoch of inflation. If these density fluctuations were unusually strong in certain regions, they could have gravitationally collapsed directly into black holes, without the need for stellar progenitors. These PBHs could have ranged dramatically in size, from asteroid mass to hundreds of thousands of solar masses. The significance of primordial black holes in the context of the Kronos anomaly is immense. If even a small population of massive PBHs existed in the early universe, they would have acted as incredibly efficient gravitational seeds. Imagine these primordial monsters scattered through the nascent cosmos, each a powerful attractor that would have pulled in surrounding hydrogen and helium gas with unprecedented speed and efficiency. This accelerated accretion would have triggered a cascade of star formation around these seeds, creating massive, metal-rich galaxies far earlier than conventional models predict. The gravitational influence of these PBHs would not only have expedited the collapse of gas, but also potentially enhanced the rate of mergers between nascent galaxies, quickly building up the observed mass and maturity of objects like the Kronos anomaly. Intriguingly, primordial black holes are also considered a candidate for at least a fraction of the universe's mysterious dark matter. If they constitute a significant portion of dark matter, their presence would not only explain the rapid formation of early structures, but also offer a compelling solution to a long-standing cosmic puzzle. Detecting direct evidence of PBHs remains a formidable challenge, but their existence might leave subtle imprints, specific gravitational wave signatures, unique X-ray emissions from accreting gas, or even distinctive lensing patterns. Some of the compact ultraluminous sources observed by Webb in the early universe, which are difficult to explain by conventional stellar processes, could potentially be active primordial black holes feasting on primordial gas. If a clear signature of PBHs can be found in Webb's detailed spectroscopic data, it would fundamentally rewrite the story of early structure formation, bridging the gap between the universe's first instance and the massive galaxies we see today. Beyond primordial black holes, the Kronos anomaly pushes us to confront an even more profound question. Was the Big Bang truly the absolute beginning of everything, or merely a transformative event within a larger, more ancient cosmic cycle? This leads us to cyclical or bouncing universe models. In these speculative frameworks, our Big Bang was not the genesis from nothing, but rather a rebound from the collapse of a previous universe, or a transition within an eternally existing cosmos. For instance, in the Big Bounce theory, An earlier universe expanded, reached a maximum size, then began to contract under its own gravity, eventually compressing into an incredibly dense state, not necessarily a singularity, before rebounding into the expanding universe we inhabit today. If our universe is indeed a product of a cosmic bounce, then the Kronos anomaly finds a radical, yet elegant explanation. Objects like this impossible galaxy could be relics or fossils from a previous cosmic cycle, structures that somehow survived the bounce, carrying with them an age that inherently predates our universe's 13.8 billion year clock. Imagine structures, perhaps formed from primordial black holes or other exotic matter, that possessed enough resilience to endure the extreme compression of a universal crunch and re-emerge in the subsequent expansion. Their intrinsic age would then refer to their formation time within the prior cosmic iteration, making them legitimately older than our current Big Bang. Various theoretical models underpin these bouncing scenarios, such as the ekpyrotic universe, which proposes that our universe originated from the collision of two branes, higher dimensional membranes, in string theory, or models rooted in loop quantum gravity that suggest gravity becomes repulsive at extreme densities, preventing a singularity and leading to a bounce. These models often predict specific signatures in the cosmic microwave background, or unique patterns in the large-scale distribution of matter that might distinguish them from the standard inflationary Big Bang model. While currently beyond Webb's direct observational capabilities, injects a newfound urgency into searching for such subtle echoes from beyond in future, more precise cosmological data. The philosophical implications of a bouncing or cyclic universe are immense. It would fundamentally redefine our concept of time, suggesting that it might not have a singular beginning or end, but rather flows in an eternal self-perpetuating cycle. The Kronos anomaly, in this light, transforms from a temporal paradox into a potential bridge, a tangible link to a cosmic past far more ancient and complex than our current textbooks allow. It forces us to consider that the universe we inhabit is not just a chapter, but perhaps a single sentence in an infinitely unfolding cosmic epic, where creation is not a singular event but an eternal process, continually recycling matter, energy, and perhaps even conscious awareness through endless iterations of existence. This journey into pre-Big Bang ideas is the ultimate frontier, where the very definition of cosmic genesis stands on the precipice of profound re-evaluation. The Kronos anomaly, whether a statistical outlier, a product of extreme early evolution, or a relic from a pre-Big Bang era, has undeniably ignited a profound crisis in cosmology. Such a fundamental challenge to our understanding of cosmic history demands an equally fundamental response from the scientific community. The future of cosmology, already vibrant and dynamic, is now being rapidly reshaped by this paradox, driving an unprecedented surge in observational programs, theoretical modelling, and the development of entirely new analytical tools. The universe's unfinished symphony has gained a powerful, unsettling new motif, and the race is on to decode its meaning. On the observational front, the James Webb Space Telescope itself remains at the forefront of this investigation. Its mission planners are extending its deep field campaigns, allocating significant observation time to meticulously re-examine the sky regions where these impossible galaxies reside. New, specialized programs like Cosmos Web, Jade's Deep, and Primer are mapping immense swathes of the early universe with unprecedented detail. These surveys aim not just to find more such anomalies, but to understand their context, how they cluster, how they interact, and how their properties vary across different epochs. By building a larger statistical sample of these early galaxies, astronomers can determine whether the Kronos anomaly is truly unique or part of a larger, systemic pattern that demands a fundamental revision of our models. Webb's powerful spectrographs will continue to analyze the light from these galaxies in even greater detail, seeking ultra-precise measurements of their chemical composition, stellar populations, and kinematic motions to refine their age estimates and reveal their true evolutionary pathways. The wealth of data flowing from Webb has also spawned a revolution in data analysis. Traditional methods, while robust, are often too slow and labour-intensive to fully process the sheer volume and complexity of information. Consequently, astronomers and computer scientists are developing an entirely new generation of analytical tools, heavily leveraging advanced algorithms and machine learning, Sophisticated neural networks are now being trained on vast datasets of simulated universes, learning to identify subtle patterns and signatures that might distinguish between different cosmological models. These AI systems can sift through petabytes of Webb data, searching for faint galaxies lost in the noise, anomalous spectral fingerprints, or gravitational distortions that betray the presence of unseen matter or unusual cosmic conditions. The goal is to extract every conceivable piece of information to ensure no subtle clue, no hidden echo of the early cosmos goes unnoticed. Complementary observatories, both ground-based and spaceborne, are joining this grand investigation, each contributing a unique piece to the cosmic puzzle. Radio telescopes such as LOFAR in Europe and the eagerly anticipated Square Kilometre Array, SKA, in Australia and South Africa, are designed to map the faint 21-centimetre signal emitted by neutral hydrogen. This signal acts as a direct probe of the cosmic dark ages and the era of reionization, charting precisely how and when the universe transitioned from a dark, opaque state to one filled with luminous, rionized gas. By comparing these radio maps with Webb's optical and infrared observations of early galaxies, scientists can precisely synchronize the timeline of reionization with the emergence of luminous structures, providing critical constraints on the speed of early star formation. The cosmic microwave background, CMB, remains a cornerstone of cosmology, and new experiments are pushing its boundaries. The CMB-S4 experiment, a massive collaboration involving telescopes at the South Pole and in Chile, will remeasure the ancient microwave background with unprecedented precision. Its objective is to detect minute irregularities in the CMB, tiny temperature fluctuations that represent the seeds of all future structures. By correlating these primordial seeds with the massive galaxies observed by Webb, scientists can test inflationary models and better understand the initial conditions that governed the universe's rapid development, potentially revealing if the initial quantum fluctuations were stronger or lumpier than previously assumed. Looking further into the future, planned missions promise even deeper insights. The Nancy Grace Roman Space Telescope, slated for launch later this decade, will conduct vast, wide-field surveys of cosmic structure, charting how galaxies cluster and evolve across immense scales, providing critical statistical context for Webb's deep-field observations. The Laser Interferometer Space Antenna, LISA mission, a proposed space-based gravitational wave observatory for the 2030s, holds the potential to detect gravitational waves from extremely early universe events, such as the mergers of primordial black holes or the violent birth pangs of the first massive structures. Such observations would provide a completely new window into the universe's infancy, potentially offering direct evidence for pre-Big Bang phenomena. On the theoretical front, cosmologists are engaged in a furious effort to build new simulations and refine existing models. This involves blending quantum gravity mathematics with large-scale cosmological simulations, attempting to bridge the gap between the infinitely small, quantum fluctuations, and the infinitely large, cosmic structures. They are rigorously testing the radical ideas proposed to explain the Kronos anomaly: self-interacting dark matter, fuzzy dark matter, evolving dark energy, and even the audacious concepts of primordial black holes and cyclical universes. Each new model is pitted against Webb's data, seeking the best fit, the most elegant explanation for the universe's precocious complexity. The James Webb Space Telescope has not merely provided images, it has presented cosmology with a profound intellectual challenge, an uncomfortable truth that demands a re-evaluation of our most fundamental assumptions. The Kronos anomaly is not just an object, it is a cosmic interrogator, pushing science to its limits and compelling humanity to look deeper, think harder, and imagine a universe far more intricate, more ancient, and more profoundly mysterious than we ever dared to conceive. The answers may lie in subtle adjustments to our models, or they may force a complete paradigm shift, revealing that the universe's story of creation is still being written, photon by painstaking photon. The James Webb Space Telescope, envisioned as humanity's most powerful chronometer, was designed to confirm the grand narrative of our cosmic origins, to fill in the missing chapters of the Big Bang's epic saga. Yet, in its relentless gaze into the deepest past, it has unearthed not just missing pages, but an entirely unexpected prologue. The Kronos anomaly, an object whose light unequivocally marks it as belonging to the universe's infancy, yet whose intrinsic age defies the very concept of a 13.8 billion year cosmic beginning, stands as a luminous paradox at the threshold of our understanding. Our journey has traced the contours of this profound enigma, from the elegant simplicity of the Big Bang model to the cutting-edge capabilities of Webb, and finally into the radical realms of scientific possibility. We embarked by firmly anchoring ourselves in the widely accepted story of creation, the universe erupting from a singularity, expanding and cooling over billions of years, giving rise to the elements, stars, and galaxies we observe. We then marvelled at Webb's unprecedented ability to act as a true time machine, its gold-plated mirror gathering the faint red-shifted whispers from the cosmic dawn. But the very data it collected, far from confirming all our expectations, revealed the impossible. A galaxy whose stellar populations and chemical maturity signalled an evolutionary journey of over 15 billion years, observed when the universe itself, according to our models, was only a mere 250 million years old. The initial rigorous scientific response was to seek explanation within the known. We meticulously dismantled potential observational errors, re-verifying redshifts, ruling out significant gravitational lensing, accounting for dust obscuration. We pushed the boundaries of stellar evolution, proposing hyper-efficient galactic mergers. We even explored subtle modifications to the invisible hand of dark matter, suggesting it might have interacted more dynamically in the early universe, accelerating the gravitational collapse of gas. Then, we considered revisions to the cosmic clock itself, questioning the constancy of cosmic expansion and grappling with the persistent Hubble tension. Yet, for the Kronos anomaly, these adjustments, even when pushed to their theoretical breaking points, fall short. They can early epoch, but they cannot explain an object that is demonstrably older than the universe it inhabits. This is not a matter of tweaking parameters. It is a fundamental temporal incongruity that challenges the very premise of our cosmic calendar. The scientific process, in its relentless pursuit of truth, has systematically eliminated the easy answers, forcing us to confront a deeper, more unsettling reality. So, is it a calculation error, or is the entire Big Bang model wrong? The truth, as often happens in science, is likely far more nuanced and profound than a simple binary choice. It is highly improbable that such a robust, multifaceted observation from the most advanced telescope ever built, repeatedly verified by independent teams, is merely a trivial calculation error. Webb's instruments are calibrated with exquisite precision, and the methods for determining both light travel time and intrinsic age are well established, even if they rely on model assumptions. Nor does this discovery necessarily mean the entire Big Bang model is wrong in the sense of being completely false. The Big Bang remains the most powerful and evidence-backed framework for describing the evolution of our universe since a very hot, dense state, the expansion of space. These pillars remain unshaken. What the Kronos anomaly, and indeed the broader pattern of two early galaxies, suggests is that the Big Bang model, in its current formulation, is profoundly incomplete in describing the universe's ultimate genesis. It may not be the absolute beginning of everything, but rather a monumental transition within an even grander, more ancient cosmic tapestry. This leads us to the most radical, yet intellectually compelling possibilities. The Kronos anomaly might be the first tangible evidence, however indirect, for phenomena like primordial black holes that acted as hyper-efficient seeds for early galaxy formation, accelerating the cosmic timeline in ways we never conceived. Or, more daringly still, it could be a relic from a prior cosmic cycle. A ghost from a universe that collapsed and rebounded, making our Big Bang not the singular genesis, but merely a phase in an eternal cosmic dance. If our universe is part of a big bounce or a cyclical model, then an object with an intrinsic age exceeding 13.8 billion years is no longer an impossibility, but a profound, albeit unsettling expectation, a fossil from an eon before our own. The philosophical implications of such a revelation are staggering. For centuries, humanity has sought the ultimate origin, a singular moment of creation that provides meaning and a finite timeline to existence. The Big Bang offered that, a cosmic genesis that, while scientifically rigorous, resonated deeply with our innate desire for a beginning, to learn that this beginning might itself be a continuation, a rebirth from an older cosmos, shatters our anthropocentric view of universal time. It infuses the cosmos with an unimaginable, almost infinite antiquity, making our present era but a fleeting moment in a story without apparent end. This realization evokes a profound sense of cosmic humility. Our scientific models, however sophisticated, are provisional maps, constantly refined by new observations. The universe, in its boundless complexity, routinely defies our expectations, reminding us that reality is far richer and stranger than our current theories can fully encompass. This is not a failure of science, but its ultimate triumph. The courage to confront the uncomfortable, to discard cherished beliefs when confronted by empirical truth, and to relentlessly pursue understanding even when it leads us to the very edge of comprehension. The Chronos anomaly forces us to ask, what does it mean for our place in this expanded cosmic narrative? If, perhaps life itself, and the conditions for its emergence, are not rare accidents, but recurrent echoes in an endlessly self-organizing cosmos. Each photon from Webb, each data point, becomes a whisper from a time when the very fabric of reality was still nascent, carrying memories of an existence far beyond our immediate grasp. These faint signals, travelling billions of years to reach our tiny blue marble, are not just observations of distant galaxies, they are chapters of our own preface, challenging us to reread the opening lines of our own story. As Webb continues its tireless vigil, and as future observatories and theoretical frameworks emerge, the quest to understand the Chronos anomaly will drive humanity to new intellectual frontiers. We stand at the precipice of a new cosmology, one that integrates observation, simulation, and daring imagination. Whether the answers reveal subtle flaws in our calculations or point to an utterly transformed understanding of cosmic genesis, one fact remains undeniably clear. The universe is a living, breathing testament to perpetual mystery. The darkness between stars is not an emptiness, but a canvas upon which the most profound truths are still being written. And in our persistent curiosity, our relentless drive to know where everything truly began, we reflect the very essence of that ancient, awe-inspiring cosmos. The story of creation is unfolding, and we are but witness to its unfolding grandeur.